That's a good right. Basketball player will sit here now.
Yeah. Yeah, well, my wife. What about coming? That was one of them.
Friday at like 9:40.
All right. So it's my pleasure to introduce Martín Farach-Colton, who will be our Karp Distinguished Lecturer. Just a quick biographical background. In preparation to enter a PhD program, he got a MD at Johns Hopkins, then his PhD from Maryland under Ahmed Amir. He was Google employee 100 plus epsilon. He was a professor at Rutgers. He co-founded Tokutek based on his some of his cache obliviousness research. Recently, he's moved to NYU, where he has an endowed chair and is a chair of the CS department. He's had multiple he's a fellow of multiple organizations. He had a Sloan Fellow, AAAS, SIAM, ACM, IEEE. He's had many best paper, test of time awards, pattern matching, data structures, memory management, which is sort of, why he's in speaking in this workshop. So, Martin.
Thank you so much. So I'm thrilled to be here. I'm looking out at the audience, and I see one of my earliest students is here, and my most recent graduate is also here. And people that I'm working with on a daily basis, and also Sampat, I believe I figured out that you are my least recent collaborator in the room. We used to write papers together 30 years ago. So it's an honor to be here. So let's get started talking about virtualization and the cost of indirection. And even though my talk is too long, please interrupt me with enthusiasm. So what is this talk about? What is virtualization, and why should algorithmicists care? And so virtual machine is a computer system created using software on one physical computer in order to emulate the functionality of another separate physical computer. And virtual memory provides an idealized abstraction of the storage resources that are actually available on a given machine, which creates the illusion to users of a very large main memory. So those are two different ways in which virtualization is used. And a lot of times they interact. We'll talk a little bit about that later on, which causes some confusion for people who don't deal with this every day. But virtualization is basically resources provided through a layer of indirection. And so the question is, are there any algorithmic consequences to indirection? There is some content of this talk which actually generated experiments and systems papers, and not one of those things is going to be presented. Not one experiment will be presented. So this is a theory talk motivated by systems. All right, so what are we going to talk about? A fairly simple, familiar model of memory, very familiar to theoreticians. And then we'll just keep adding detail and modifying the model as we go. That's the main thrust of the talk. So what is the simplest theoretical model of memory? It should be familiar. I think Kunal talked about this earlier on. You have a fast memory with k slots. You have a slow memory with an unbounded number of slots. And some of these guys are also copied over here. And so you also have a request sequence. And so maybe you ask for B, and you find B in your cache, and that's called a cache hit. And then if you ask for U isn't anywhere over here, so you find it over there, and you put it in an empty slot, and that's a cache miss. And we'll have another cache miss, and now this is full. So what happens when we have another cache miss? Well, now we introduce the paging algorithm, and what it does is it decides who to evict. And it evicts that guy, and that's where we put this guy. All right, pretty straightforward. The goal is to design a paging algorithm that minimizes the number of cache misses, and that's called the paging cost. All right? So this problem was defined in Slater and Tarjan 85, the paper that introduced online analysis. It was understood before then, but I'm going to give them credit for it. And so you're given an eviction algorithm, well, you design an eviction algorithm, a cache of size k, and a sequence of memory accesses. I'm going to have different cost functions. So I'm calling this one ST for Slater-Tarjan. So the Slater-Tarjan cost of a memory access is 0 if the thing is stored in the cache when you need it, and it's 1 otherwise, and the cost of a sequence is just the sum of the cost over all the entries in the memory access sequence. Is that clear? Great. So then the competitive ratio of an algorithm is the maximum over all sequences of the cost of the algorithm divided by the cost of the offline optimal eviction algorithm. Yes?
What do you think about the initial condition of cache?
Let's say it's empty. For both opt and for A.
Sorry, is this optimal algorithm node, or is this some conjectural thing? I don't understand.
If you have the entire sequence, there is some optimal algorithm. It turns out that the furthest in the future is optimal for offline. So whenever you need to evict someone, you can look at all the guys that are there, and you can say whose next reference is the farthest away, and it is optimal to evict that one.
Oh, I see. So it's not a real life thing.
It's not a real life thing. You can't actually implement this optimal one. You'd need to know the future. Clairvoyance would allow you to implement that, but yes, that's right. So the question is, how well can you do online, having to make decisions as you go, compared to this guy over here that knows the entire future? It's a pretty tough standard to meet. Yeah. So they proved, Slater and Tarjan proved that any deterministic eviction algorithm has a competitive ratio of at least k. So that seems pretty terrible, because k in real life is, usually a couple of million. So that's bad. All right. But then they had this very clever idea, which is called resource augmentation. Give A twice as much memory as opt. And now let's compare them. So now we're going to compare how well your algorithm can do if it's given an advantage. Opt has a huge advantage. It gets to see the future. So this seems like a doable advantage, right? Just buy some more memory. So let's look at least recently used. LRU is evict the page that was referenced least recently of the ones you're looking at. And they proved that the cost of LRU using 2K memory on any sequence compared to opt using K memory is at most 2. That's pretty amazing. That means you can buy clairvoyance by adding memory, right? Doubling the memory will allow you to approximate how well you could do if you knew the entire sequence ahead of time. that's amazing. And then people touted this as an explanation for why LRU works well in practice. But the story is a little bit more sad than that. Life is full of bitter disappointments. So what is the bitter disappointment here? FIFO, first in, first out, evicts the page fetched least frequently. So you just queue in pages and then you just throw out the one you fetched, even if you're using it all the time. You ignore the usage pattern and you just evict things in a first in, first out order, and this works terribly in practice in most situations. All right. What's the disappointing thing that they proved? FIFO, if you give it double the memory, does no more than twice as much as opt if you give it K memory. So what gives? Maybe the whole resource augmentation thing isn't that useful, right? Maybe it's too blunt a measure of performance. Even empty on full, you fill up your cache, and the minute you fill up your cache, you empty your cache and start over again. It also has this property. Are they sharp? I think they are sharp. Yeah. I mean, I think this equals 2. Oh, because I'm lazy. This is called weasel. Did I go back and look and think, is this actually tight? I'm pretty sure it's tight. 2 minus 1 over k or something like that. Yeah, 2 minus 1 over k. Okay, so, all right. We'll see that it's actually still a great idea, but we have to be a little bit more careful. That's the conclusion, one of the conclusions that we're going to have. So this paging problem and beyond worst case analysis. Beyond worst case analysis is awfully trendy. And the good news, bad news about resource augmentation is that it inspired a large literature of beyond worst case analysis. And I put the citations for the earliest papers I could find on each of these different directions. One direction is restrict the adversary. In this line of work, you have access graphs. And if you fetch a page, the next page you request has to be one of the neighbors, and so you can move around the graph. And they prove that LRU is much better than FIFO if you have tree access graphs. And then there was a whole huge literature since '91 on this line of work. Then there's this biased adversary, bounded bias adversaries by Katsoupias and Papadimitriou. And don't need to get into the details of what it means to be a bounded bias adversary, but LRU is shown to have optimal behavior and FIFO much worse. So these are all attempts at trying to tease apart why LRU should behave well and FIFO should behave badly. A lot more recently, smoothed analysis came in, and smoothed analysis, maybe these bad cases that get you to 2 minus 1 over k have to be very particular, and if you fiddle with them, if you shake them up a little bit, add a little randomness to them, the worst cases break. And they showed that that was true of LRU and it's not true of FIFO. FIFO can be robustly bad even when you fiddle with it, and LRU, the bad cases are very particular. So these are all sort of a line of research on trying to get around this resource augmentation. And we're going to look at a different way to deal with this limitation of resource augmentation a little bit later on in the talk. Good? All right, so far we've talked about the paging problem. Guess what we're going to do as the talk goes on? We'll fill in the puzzle pieces. All right, so now how does virtual memory change the paging problem? Virtual memory, you allocate a piece of memory and then you make reference to it. And why do we use virtual memory? Because physical memory address space is complicated. You can have pieces that you can use and pieces you can't use. Some things can be on disk way over here and other things inside of RAM, and it's a mess. And so what you do, and you need it because you want to maybe be able to share memory between processes, or you want to isolate each other, the processes' memories from each other. You want to swap to disk without the programmer needing to worry about swapping to disk. Let the operating system do that. And these are all reasons to have a layer of indirection between what you were referring to. This pointer is just an address in the virtual address space. And then this layer of indirection tells you where it actually is residing in real reality. It's very much like when you write a recipe. You don't say, pull the whisk out of the third drawer on the right. You say, use a whisk. And there has to be an indirection table that tells you where your damn whisk is. And it might be different in each person's kitchen. It might move around from place to place in your kitchen. And now it's in the dishwasher, right? So this is just like writing recipes. You just say, whisk the eggs, all right? So this process here, every virtual memory reference needs to be converted into a physical address. Every single one, every time you do it. All right. So now I have slow memory. I've coded them this sort of mauve, and then the stuff in RAM. I've this bilious green. And now I've added this address translation table, sometimes called a page table. And that's just this layer of indirection. The ith entry here is where you can find the ith virtual address. It points to the physical location of the page. So virtual address 1 is at disk position 1. Virtual address 2 is at RAM position 2, and so on. Good? Just a simple indirection layer. In reality, we'll see how this is actually implemented in practice, but that's what's going on. And so now if I reference the 5th virtual address, I go to the 5th entry, I see that it's in the 6th RAM position. If I go to virtual address 1, it's at disk position 1, and I have to fetch it in. And now it's also in the 3rd position of RAM, and I have to update this entry, because of course I'd rather find it in RAM than on disk. That would be much faster. All right. So now we have an eviction algorithm, a cache, a memory access sequence, and tau is the cost of this address translation. Yes?
Be a stupid question, but is it completely obvious that there's no advantage having the virtual memory reference itself?
The virtual memory reference
It
itself.
sounds like it's obviously stupid, but I don't know if it's obvious.
Well, you actually need to, at some point, get to the thing you're referencing. So I don't know under what circumstance you'd have like a chain of virtual addresses that then get you to a physical address. But
It might allow for some branching.
you know, since I do have an MD, what I learned by studying biology is that the answer to is there a biological system that does X is always yes, even if it violates the laws of physics. And as a theoretician working with systems people, I've learned the same thing about systems. So I'm going to say yes, there's such a system. All right. So the cost of virtual memory is tau if it's in cache, because I had to do the address translation, and it's 1 plus tau otherwise. This looks like a very stupid thing to model, because it's just tau plus our old cost, which was either 0 or 1. I've just factored out the tau and rewritten it this way. And so now the virtual memory cost of a sequence is n tau, because I've made n memory references, plus the cost of paging. So that's the cost of address translation, and that's the cost of paging. Is that clear?
But tau is a constant? This is simplifying, right?
Is tau a constant? That's a great question.
You may have a TLB miss or something. Can it be different?
My goodness, you've just anticipated 85 of my slides. Raise your hand if you know what a TLB is. Raise your hand if you don't know what a TLB is. There were several people who didn't raise your hand either time, so you're in some superposition of knowing and not knowing. We're going to get to TLBs. Let's chill out. All right, so this cost is independent of the paging algorithm, and this is just the cost of the page induced by the paging algorithm. So there doesn't seem to be a new algorithmic problem here. And also, is this even important? Like tau, surely tau is very small. Do we need to even worry about it? Yeah? All right, so without special hardware, it would be more than 90% of your execution time on a program that doesn't do a lot of swapping. Like, it's expensive compared to your arithmetic. And chips have special hardware. What is it? Do you have any suggestions for what we should call the special hardware? The translation look-aside buffer. It is often very sad not to be the first person to write a paper on a topic, because then you're stuck with whatever name they gave it. That's a terrible name. What's this look-aside doing there? I don't know what that's, like, it's the translation cache. All right, it's the TLB, which brings the cost of this address translation down to maybe as low as 5%, but on lots of things, you still get 30 to 70% of the total cost of running a program is address translation, even when you add translation look-aside buffer, which we now have to explain what it is. What is it? And does it involve any fun algorithms? We only care about systems if we get to do algorithmic work, right? Can we all agree on that? All right, it's a chunk of the motherboard for looking up virtual to physical addresses translations in parallel. So this is a simplified view of what it is. And so it looks at all these entries in parallel, and so you can store virtual physical pairs in there. And I come up with a virtual address, and I go, and in about one clock cycle, it just tells me what's the physical address that matched. So is this just a cache for address translation? And if it's just a cache for address translation, why don't you run LRU for pages in RAM and LRU for translations in your TLB? This is, so far I've been promising algorithms, and it's just one failed attempt after another. So there's a systems motivation for more theory. Lookups take about one clock cycle, and the fact that this is parallel implies that the bigger you make it, the more parallelism you need to implement, the hotter it runs. If you make it too big, it will melt your chip. And so what is not too big? On this chip from 22, the fastest TLB had 96 entries in it. 96 entries for RAM that has a couple of million pages in it. And it's not growing very fast because it's hot. And so the algorithmic consequence of this is you don't get to do any resource augmentation on it for sure, because try telling a computer architect, oh, no worries, we'll just double the size of it and then it'll run great. They'll tell you, we've been working for decades and we got up to 96 entries. All right. And so the bottleneck for performance is the extremely low % of RAM that a TLB can cover, right? 100 entries out of millions, yes.
Get to huge pages at some point?
We definitely are. Maybe even very soon. I love the enthusiasm. All right. So We have this address translation table. We have the TLB that maps from virtual addresses to physical addresses. These are all in RAM. And so now the cost is, as you wanted different costs, if it's in the TLB, it costs epsilon. If it's not in TLB, but it is in cache, it costs tau. And otherwise, it costs 1 plus tau. And then you sum it up. And so this is gross, because I'm just added more details, but no new algorithmic stuff. All right, so that's virtual memory and TLBs. But all is not lost, because a TLB is not a cache. A TLB is not a cache. And this is where we're going to start getting into design stuff. What is a cache? It's a place to store items for easy access. Cache is one of those words that means the thing and its opposite. So it means a thing where you have it for easy access, and also a thing where you hide it away. So in this case, it's the easy version of a cache. What is a TLB? It's a general purpose key value table that runs in parallel. Why isn't a TLB a cache? A cache would be restricted to only storing virtual physical pairs. And what else could you store in a TLB? Anything you want that helps compute address translations. So let's figure out what are some choices. Well, here's the picture we had before. Suppose you get lucky and you find a run of physical pages that are also a run of virtual addresses. Then you could encode, this is quite small. I was snarkily complaining to one of my friends who was sitting next to me earlier on in a talk that the youngster who was giving the talk was going to increase their font size when they hit middle age. And here I am doing even worse job, and I think I'm no longer middle-aged, so shows I'm a hypocrite. Okay, virtual addresses 1 to 4 start in position 3. And so if I need to find where virtual address 3 is, I go to position 3, and 3 minus 1 is 2, because I want the third, and the first one is 1, so it's 2 positions along, so it's at R5. A little simple arithmetic, and a pointer to the beginning of the run. Well, that is not literally a virtual physical pair, and it encodes a bunch of these pages all in one entry. That's called a huge page, so Phil is now satisfied. This is called retail talk giving. I'm going to make each of you happy one at a time. The pros of this is that you get a larger effective TLB, and programs often have a lot of virtual locality. If you access a page, you are very likely to access a nearby page. And the cons is this is never going to happen by chance. And so it's up to the paging algorithm to make this happen. The paging algorithm is going to have to make this arrangement appear so that you can put in one of these entries in your TLB. Yeah.
I've never seen this before.
Sure, yeah.
So what is this actually doing, this TLB?
The TLB is translating from something, in this case, it's a range of virtual addresses, to some location in this case. Like this coding is, it goes from, like you drop the low 2-order bits of the virtual address, and you look that up, and then it tells you that starts at the 3rd position of your RAM. And so now you know that the next 4 positions are sequential in virtual memory order. You can look them all up using this one entry. So if I look up virtual address 1, it'll go here. I'll do some arithmetic and get there. If I go to virtual address 2, I'll go here. I'll do slightly different arithmetic and end up there. 3, 4. They all can be encoded using this thing because I have virtual and physical addresses in order because I've arranged these all together in a row in RAM. Does that help?
Approximately.
approximately helps.
So this picture sort of shows like a huge pages could be of any size. Like not all huge pages need to be the same size, according to this picture.
According to this picture, but we're going to
In
get
practice, I know there are like two sizes. So
two sizes, and we're going to see why that is. Later on, I'll make you happy. This is so good. What's your question from slide number 72?
What you do in the TLB affects the epsilon, does it?
Yes. Well, it affects how often you hit the TLB.
But it also could impact the epsilon.
The epsilon is not changed.
It's not an epsilon.
No, it doesn't change the lookup time of the TLB. It changes the amount of coverage of the TLB. If this covered 1 million pages, then that's half your RAM. So you'd think that about half the time you'd hit that. Maybe not in the worst case, but in practice.
So basically, do I understand correctly that this is where the algorithms come into the picture?
Almost, yes, that's right. How are we going to, now we have to get a paging algorithm to do good stuff, to make this arrangement. But actually the algorithms that I want to get to are a lot more interesting than this one. But we're going to go over these algorithmic part. All right. So I've claimed that, did I say this? Increasing huge pages, making huge pages increases the total amount of paging that you do. And that's for 2 reasons. You might want to coalesce pages into a huge page, so then you need to move things around inside of RAM and maybe evict some pages that are in the way, because you got to put them all right next to each other. And then you get more paging. Or maybe you never use page 3, but you got to go fetch it, because to have a huge page, you have to have all your physical pages in virtual page order, right? And so you got to fetch that guy. That's a wasted I/O, and you now have someone taking up a slot that you're never going to access, so it reduces the total amount of memory for that you could have used for other pages that you're going to use. Okay. So huge pages, this is called internal fragmentation. That's called external fragmentation. Doesn't really matter what they're called, but they increase paging. And they are used in practice, although we found at my database company that if people had huge pages on, their performance would suck. So our software would not load unless they had booted up with huge pages turned off. We forced our clients to turn off huge pages in order to achieve performance, and that is not uncommon. And so they are used in practice, but they sort of suck. So there's a huge literature on trying to make them work. And so like I could have filled up this page many hundreds of times of papers trying to make huge pages work in practice. And so there is this big open problem. Is there an algorithmic way to mitigate the expense of having huge pages? And I don't think anyone's done a very careful model where they can actually figure this out. And you would be the hero of the systems world if you could make this work, because, like I say, the number of papers on this topic is huge. So where are we now? We have 2 algorithmic handles. We can encode TLB entries, and we can modify the paging algorithm. And we've already seen that this is actually one thing. These are co-designed. You modify the paging algorithm in order to allow you to change your TLB entries. So are there more interesting codes?
Sorry, I have a question regarding
yes.
that. Regarding those 2 algorithmic handles, I'm confused what happens where. So the paging algorithm definitely happens in software and operating system, but the encoding of the TLB entries should be happening in hardware, right?
Yes.
So then those 2 are not even designed by the same people, not even close people, right? So
therefore, when you write a paper on this topic, you get 16 authors.
Okay.
Raise your hand if you're a co-author on this paper. Well, you are. You are. Okay, we have 3 of the co-authors, but we're only missing 13. And I think they were at 8 different institutions. So, yeah, you need architecture people, you need operating systems people, and you need algorithms people. 100%. And you need to run hardware simulations, and you need to modify Linux and run those simulations, and you need to prove theorems. And guess which ones of those I'm going to show you the results of today? Theorems. All right. So 100%. And it also took 2.5 years. It was.
May I ask you?
Yeah.
The open problems that you mentioned, previously is how to come up with a cost model that will precisely somehow express how a system works, and this is the difficult thing that we
No, I think that's probably not the difficult thing. I think
because in your cost model, the one is not to manage. Now you have huge pages, you pay more cost, it depends on the size, then sometimes you pay the tau, some others you don't pay the tau and the epsilon, so it becomes more complicated.
it becomes, all right, so the question is, what's the hard part in the open problem? Is it modeling the cost of huge pages, or is it coming up with a paging algorithm that lets you more efficiently do huge pages?
Since this is an open problem, why aren't there people trying to show there is no good answer?
That would also be an awesome result, but I think it would be a not especially surprising result given the number of smart non-theoreticians who have worked on it. And I'm not saying that like only theoreticians can do things. I'm saying that like smart systems people have different fish to fry, and lower bounds are not really their thing to prove. That's for us to prove, if anyone's going to prove it. Yeah. So, yeah, a lot of smart people have worked on it, and they continue to work on it. It's one of these things that when you solve a problem, there's one solution, and when you have 20 different solutions, it's because you didn't solve the problem. That's where we are with huge pages. Yeah. All right. All right, now I'd like to tell you an algorithmic tool we do have, which is tiny pointers. How big is a pointer? All right, so physical address and a TLB are nothing but pointers into RAM. And RAM holds k items, so a TLB physical addresses need at least log k bits, right? There's not much to it. You need a log of your address space to encode a pointer. So a bunch of the rest of the talk is how to encode physical pointers using fewer bits. We're not, even though they are pointers, and pointers seem to like incontrovertibly take log of k bits, turns out that in interesting cases you can use fewer than log k bits. And this will be one of those interesting cases. So the question is how and why. Let's do the why. We started out here with this huge page, but now we're going to, what if you could use fewer than log k bits per physical address? Then you could replace this one pointer to the beginning of a run to a little array of teeny pointers. So the first position is in position 4, and the second address is in position 3, and the third address is in position 9, and the fourth address is in position 7. Right? This range of virtual addresses is encoded by this array of what will be tiny pointers that use very few bits. And so we could just write them all down in the TLB without using any more circuitry. Seems impossible, at least infinitely improbable. So that's going to be let's figure out how to do that. And then
Control the paging of it, right?
you do.
You can make it so there's lots of really small.
You can try to. Yes. Well, they're not going to be clustered. That's not what we're going to do.
But then, when you have a page code, you have to go to some other data structure to find out
Absolutely. And then when you write the paper, you have to show that that data structure can be implemented in hardware and run in parallel with your TLB entry and not take any longer than the TLB entry. I'm not going to talk about that. All right, so they don't need to be together or in order. And so that gets rid of the paging of coalescing them and things like that. But in fact, you have this other advantage of, oh, well, I'm never going to use the second one of those. I don't even need to have it. I don't even need a pointer to it. I don't need to fetch it into RAM. So that was the other reason that we had paging, is that we had to fetch useless pages. So if we could have these itty-bitty pointers, we would not need to do either of these expensive swapping paging operations. Yes?
Is each of those pointers pointing to just exactly one page?
Yep. So tiny pointers seem to solve the extra paging problem of huge pages. So what's known about tiny pointers? Well, tiny pointers versus pointers, you malloc and get a pointer, and then you dereference the pointer, and you can set a value, and you can free it. And what we're going to do with tiny pointers is you're going to malloc with a key, and it will return fewer bits. And when you look it up, you have to provide the key and the tiny pointer, and now you get the location. And you can set values, and you can free up the memory. So obviously, just information theoretically, you need log k bits. And so we're going to use some key to absorb some of those bits. And we're going to see what that key is later on. It's something we already need to store. Maybe if you think about a TLB, you can think about a thing that we already have to store that we just get for free and don't need to waste space on. All right, so this seems impossible, so let's have a very simple example. Suppose you had an array that I've broken up into a two-dimensional array where each of these buckets have polylog n size, and so there's n over polylog buckets. And whenever I want to insert a pair xv, I hash to some bin h of x. So I hash according to the key. That takes me somewhere. And then I find an empty slot and I store v there. And then I return the position, the offset. So this is 0, 1, 2, 3, 4. Yes, sometimes my offsets start at 1 and sometimes they start at 0. That's because I'm exactly the right age to go from Pascal to C. And I'm never going to get over it. OK. All right, so now 4 plus x, if I give you x and 4, I can find this entry. And 4 is not going to have many bits. So the n balls can be thrown into this array without any of these guys overflowing if I just make it slightly bigger. And the total space is like n plus n over log n. And I can make the parameters work out so that if I throw n things in there with high probability, nobody overflows. They'll be very evenly divided. And so if I have a query with x and a tiny pointer, I go to h of x, I go up to the pointer, and I can return the value I find there. Yep. So now, so far, if these tiny pointers are offset in a polylog log size bucket, and so I just gave you a scheme with log n bits per pointer. Yeah? I've shrunk from log n bits to log n bits. And there's not very much extra space that I needed. Instead of having an array of size n, I have an array of slightly more than n. All right. So yeah. This is not what we actually do. This is a warm-up to what we actually do. So for a pointer, it has arbitrary associativity. When I do this malloc, I can return any piece of memory. And for tiny pointers, it has low associativity. There are only a few places I could have be pointing to. So the associativity is the number of locations an item can go to. And so low associativity with a small probability of allocation failure. That's the guarantee that you get from this kind of system. And the smallest a tiny pointer can be with space 1 plus epsilon n is poly epsilon log n. And so that gives you pointers that's log of this. So log n plus log of 1 over epsilon bits. About log n bits. And you can't get any smaller than that. So that's surprisingly small. Log n is a very small number. Let me just say that you might think this is all highly theoretical, but people are starting to use tiny pointers to actually, like in database and systems papers. In fact, someone has a paper with tiny pointer-based hash tables that's going to be submitted tomorrow, right?
Hopefully.
They actually, there's no like weird giant constants or anything.
What does it mean allocations work with high probability?
And sometimes you will say, please allocate this piece of memory, and with polynomially small probability, it'll say, oops, and fail.
And that's just because one of those hash buckets fills up?
Yep.
Okay, yeah, thank you.
Yeah. Oh, I'm sorry. You were asking the question of under what circumstances.
Yeah.
Yes. Okay. All right. So there's an open problem for these guys. How do you use them in graphs? Well, because when you look something up, you need this key plus the tiny pointer. So you need to know the key. And if you're in a tree, you might have a pivot at a node or some particular piece of information at a node. And you can use that as your key because you're storing it already anyway. And so using it as the key isn't going to waste any space. But in a graph, you have to have lots of guys pointing to the same thing, and they all have to know the same key. And so there's this open problem of how, under what circumstances can you use tiny pointers in a graph where people have to share a pointer. It's part of the problem is you can't share a pointer. All right. So tiny pointers are the right direction, but not exactly what we need, because they are low associativity with a small probability of allocation failure. But we have to design a paging algorithm. So we want a low associativity paging algorithm with small probability of extra paging. And that's what we'll design next. And I'm going to hurry up. Low associativity paging. Is this the same as paging on a low associativity cache? So almost all caches in the world have low associativity, and almost all theoretical results apply to fully associative caches. And so how does paging work on a low associativity cache? And can we design very low associativity cache where we can page very well? Those are the questions. So let's start by examining the most common type of hardware associativity constraint, set associative caches. What is a set associative cache? It's a partition of the cache. Any page can map to a single partition, and then you can put it in any position of that partition. And so the associativity is the size of one of these partitions, because that's how many places each guy can go. And yeah, so set associative cache has sets of size D. And almost all hardware in the world is either fully associative with some warts or set associative. Those are the two common patterns. And how does associativity of a set associative cache affect the amount of paging? You would think that given the number of set associative caches, someone would have figured out whether it blows up the amount of paging that you have to do. And first question is how we should measure paging. The previous work measured fully, like the common thing was fully associative algorithms versus fully associative opt. This is not set associative. Limited associative algorithms versus limited associative op. This baseline doesn't help you tell how much you lose by becoming set associative. Competitive analysis where you have a distribution on the pages, and how do you know whether the distribution is realistic? So what we want is to compare ourselves with LRU, not against this mythological opt, because LRU we already know is good. And we're not going to be losing these factors of 2 against opt, because if you told the systems person, don't worry, your system will only do twice as much paging as it could, they would not listen to anything else you have to say. But if you tell them it's very close to LRU, they might listen to you. So how close? Very close to 1, and you only get a tiny amount of resource augmentation. Now we're talking. We need tight bounds against LRU. That's the comparison that I think is the useful comparison. And so there's this very interesting phenomenon. If you have a slightly more than log way set associative cache, then you are 1 competitive against LRU using a tiny amount of resource augmentation. So that's super interesting. You can shrink the associativity almost all the way down to log and still have basically the same number of IOs as LRU if you just have a teeny amount of resource augmentation. And if you're slightly below log n, then you are not constant competitive against any polynomial resource augmentation. So you could have extravagant amounts of RAM. If your set associativity is a little below log n, you're hosed. There's no constant that'll let you match LRU. So just above log, you're 1 competitive, and just below log, you're not constant competitive.
Does this mean you're just doing LRU within each of those sets?
Yes, right. Yeah. OK. And as a side note, when we actually tried to look at constants around this, almost all caches that we could find are just a little bit too small to be in this regime, which is sad. All right. And so you could use this for a paging algorithm. The paging algorithm could pretend that RAM is set associative, right? It could pick one of the sets and make it slightly bigger than log, each one. And then we would have physical addresses with log k bits. And we wouldn't be doing any extra paging.
Where's the probability coming in? Are you mapping? Are you using a hash function to map the address space or something?
Yeah. You pick which set you're in at random. Yes.
For the resource augmentation result, does the set associative cache have to use the extra resources with the same associativity scheme, or can it use it as a fully associative cache?
That's a great question, which we will not exactly answer, but get to in just a second. In this scheme, you just get a few extra sets. All right. Can we do better? How low can you lower the associativity of a cache and make it basically 1 competitive with LRU? If you pick 2 sets at random and do LRU on your 2 random choice of sets, then you can make the sets have log size. And this, for those of you who know balls and bins analysis, is closely related to the power of 2 choice analysis of balls and bins. And this yields physical address pointers with log k bits. And our practical system uses this one. Sort of. Almost this one. And then what happens at even lower ones, you can define DLRU as pick D uniform random choices in LRU amongst all of them. So here I have 2 LRU. It maps to these 2 random locations. This one's cold. I haven't touched it in a while. This one's hot. I've touched it recently. I replaced the cold one with this guy. And LRU is not alpha competitive with beta resource augmentation versus fully associative LRU for any constants alpha and beta. You need a lot of resource augmentation, and you still get pretty terrible competitive ratio, not constant. But it is a popular heuristic. What about this worst thing, D random? Now I'm just going to pick the locations. I'm going to ignore which one's been recently accessed and which one is not. I'm going to flip a coin. This is a Canadian loonie in preparation for my escape from the United States. Pick one at random. It could have been the one I've been accessing all the time. And surely 2 LRU is better than 2 random, right? This looks terrible. You're just ignoring the frequency of access of pages. You're just ignoring everything. But 2 random is constant competitive with fully associative LRU with constant resource augmentation. So it is actually better in the worst case. And can you do better? You can combine. You can have a front yard where you run 2 random, and with some small probability you drop to the backyard and you run set associative LRU. And for this one, you can get 1 plus epsilon competitive with 1 plus epsilon resource augmentation with poly 1 over epsilon associativity. So plugging in a slightly super constant amount for D, you get 1 plus little o of 1 competitive with 1 plus little o of 1 resource augmentation against LRU. So you can bring the associativity almost all the way down to constant and still be extremely competitive with just regular fully associative LRU, which we were extremely surprised by. So the consequence is that you can specify the location of any page in cache using a slightly super constant number of bits without blowing up the paging costs. All right, so that's tiny pointers. And so now we had tiny pointers. We came up with low associative paging, and we noticed that paging gives tinier pointers. Like this was bounded at log, log, log. Here you get down almost at constant. And so you can pack in almost log k pointers in there and have each one of them be a very small number of bits. And you can do it by modifying the paging algorithm to do this very careful paging that will allow you to pack all of these bits in there. And then when you measure it, it actually works really well in practice. And in fact, it works so well in practice that there's a chip being built using this scheme. So, a yet-to-be-named company. The tiny pointer open problem, how do you share tiny pointers? And here, how do you share part of your virtual address space? Maybe 2 processes want to point to the same library, but those libraries reside in different parts of their virtual address space. And so because you use the virtual address as this key that you're going to hash, and you might need this for inter-process sharing. So, historical aside, are tiny pointers the chicken or the egg? Which came first? Tiny pointers or all this mess with TLBs? The first thing that came was tiny physical addresses for address translation. This was an ASPLOS paper in 23. It got a Best Paper Award there. Here are the 16 authors. OS, Theory, OS, I don't know, some of these guys are also architecture. And then from there, we came up with iceberg hash tables, and from there we came up with tiny pointers and this other thing called partition hash tables. So in fact, these theory things in like JACM and SODA and so on all came from this consideration of how TLBs should be encoded. All right, a last few notes on the strangeness of address translation. It is a very strange process. The address translation table is actually a degree 512 radix tree. So it's a tree with branching factor 512. And you need to keep track of things in RAM, but also things on disk. So the number of translation in the table is n, which is all the used virtual pages, not just the size of RAM. And so the cost of address translation in theory is log n if you miss the TLB. And that means it was depth 4 before. We're moving to depth 5 nowadays. And so the cost of TLB miss, there's some missing words there, is going up. It's hundreds of times slower than a TLB hit. So why don't we just use a hash table for this thing instead of this tree? The radix tree is implemented as a combination of hardware and software. And it's been that way since the 80s. And so changing the data structure requires changing the new chips and changing a lot of different parts of these chips. And showing that it's worth switching the data structure means showing that it'll be better despite decades of hardware optimization. So there's just a lot of sunk cost into making this worse data structure work as well as possible. And so you've got to overcome all of that in your very first design. All right, that I think. So we've sort of run out of optimizations for hardware optimizations for these page tables, but other parts of the chip keep getting optimized. So the time is right for a big data structural push to replace these radix trees. Remember huge pages? If you measure how much virtual locality there is in a typical program, they should be about 16 to 32 pages long, because beyond that you start losing this sort of benefit of virtual locality. But there are 512 pages long. Why? Because they're implemented by trimming one level of the radix tree. That's it. The tree is branching factor 512, so you were stuck with gathering 512 pages together. It's sort of catastrophic. Sometimes they trim 2 levels and you get however much 512 squared is. 2 to the 18, whatever that is. You're supposed to know this, Rob. A gig. All right. So huge pages are too huge. I already told you that at Tokutek we made them turn it off. So the biggest weirdness of all is, so far I've only been talking about virtual memory, but there are also virtual machines. And the real machine emulates all memory accesses of the virtual machine. It emulates the TLB. It emulates the address translation table. In the cases where there are no TLB hits, each access to the address translation table node in the virtual machine is an entire tree traversal in the real machine. So in the worst case cost of address translation in a virtualized system is log squared, which in practice takes your number of memory accesses from 4 to 25. It's a crazy, crazy thing that I actually didn't believe and had to be browbeaten into me by systems people who assured me that it was true. All right, so maybe I sound pessimistic about change, but TLBs are also highly hardware optimized, and it is possible to have an impact on practice, in this case via algorithmic. So the real question is there an incremental path to fixing this colossal dead end that we find ourselves in with respect to something that can take up over half of your computational costs. So that is all the pieces of this talk. And with that, I thank you. Any other questions? Well, there were lots of questions along the way, so thank you. Oh, tell me your question.
So we've had virtual memory or caching around for so many years.